Open up Irodov's Problems in General Physics, and you will find that problem 1.4 stands out. Most kinematics problems hand you a paragraph full of initial velocities, accelerations, and time variables. This one gives you almost no text and zero equations. Instead, to solve this problem, we have to extract every piece of kinematic data we need directly from a single position time graph. This chart shows the distance traversed by a point over 20 seconds. We have distance, s, on the y-axis, running from 0 to 2 meters, and time, t, on the x-axis. The particle's journey is mapped by this s-curve. To find our answers, we rely on one core principle. The physical velocity of this object is directly represented by the mathematical slope of the curve. By relying on geometry, we can skip complex calculus derivatives entirely. We just treat the graph like a visual puzzle. Let's look at part A. We need to calculate the average velocity of the point during its entire time of motion. We start by identifying the boundaries of the journey. The motion begins right at the origin, 0, 0, and concludes at the 20-second mark, where the distance reaches exactly 2.0 meters. To find the average velocity across this whole period, we draw a secant line, a straight line connecting these starting and ending coordinates. The slope of this line is our average velocity. We calculate it by taking the total change in distance, our rise, and dividing it by the total change in time, our run. Dividing 2 meters by 20 seconds gives us exactly 0.1 meters per second. Notice how this secant line cuts right through the S-curve. Average velocity only accounts for where you start and where you finish, ignoring all the speeding up and slowing down that happens in between. Part B asks for the maximum velocity. Now we are looking for a specific instant in time, rather than an average over 20 seconds. Geometrically, instantaneous velocity is represented by a tangent line, a straight line that just grazes the curve at a single specific point without cutting through it. Because a steeper slope means a higher velocity, we need to locate the steepest section of the entire curve. As we slide a tangent line along the path, the angle rises, hits a peak right around the 10-second mark, and then begins to flatten out again. We lock our tangent line at that steepest point to calculate its slope. To do this accurately, we look along the tangent line for 2 places where it intersects the grid exactly. Reading the grid, we can isolate a segment of this line with a rise of 1 meter over a run of 4 seconds. 1 divided by 4 gives us a maximum velocity of approximately 0.25 meters per second. By treating the graph geometrically, we located the maximum instantaneous velocity just by finding the steepest slope. Part C presents an interesting condition. We need to find a specific moment in time, let's call it t0, where the instantaneous velocity is exactly equal to the mean velocity averaged over those first t0 seconds. We can translate that requirement directly into geometry. We need a tangent line, representing instantaneous velocity, that also passes directly through the origin, representing the average velocity from the start. The easiest way to solve this is to anchor a straight edge at the origin, 0, 0, and slowly pivot it upward until it just barely touches the upper half of the curve. Right there. That specific point of contact is the only place on the graph where a tangent line also connects back to the start. Now we just need the time value for that exact moment. We take our point of tangency and trace a path straight down to the horizontal axis. Reading the axis, the line drops down precisely at 16 seconds. So t0 is 16 seconds. What sounds like a complex calculus problem on paper is solved in seconds just by aligning a line on a grid. Here's our complete geometric map for problem 1.4. The secant line gave the total average velocity, 0.1 meters per second. The steepest tangent revealed a maximum velocity, 0.25. The anchored tangent pinpointed our time, 16 seconds. Kinematics is a highly visual subject. If you remember that secant lines reveal averages and tangent lines reveal instants, you can extract precise data directly from simple curves. Now that we have a solid grasp on extracting velocities graphically, we can apply these tools to multiple objects moving at once. In the next video, we will look at problem 1.5 and tackle relative motion and particle collisions.